Hello, everybody. Welcome, welcome, welcome to the WHPI workshop. I'm going to go ahead and start sharing my screen. And Kelvin or somebody, Barbara, can you confirm that you can see my screen in the proper presentation mode and you can hear me?
I can see your screen, and I can even introduce you. Everyone, this is Sarah Gibson. She's one of the lead organizers of this workshop, and she's going to give you an introduction to the workshop purpose and what it's about, and also some of the rules of the road for the workshop.
Thank you so much, Barbara. Okay, on behalf of the WHPI Scientific Organizing Committee, who you see here, I'm very happy to welcome you to this WHPI workshop. The Whole Heliosphere and Planetary Interactions, which is of course WHPI, is an international initiative that is focused around solar minimum. And it aims to understand the interconnected sun, heliosphere, and planetary system. Of course, WHPI is following two similar initiatives during the two previous solar minima. And with each initiative, we've been expanding our scope from the sun, solar, wind during whole sun month of 1996 to sun, solar, wind, geospace science during whole heliosphere intervals of 2008, 2009. And now, of course, with the study of sun, solar, wind, planetary interactions during WHPI. So the success of these efforts relies on a broad participation of scientists worldwide and across disciplines. In other words, all of you. And, we're disappointed we couldn't hold this meeting in person as we had planned originally. But on the other hand, by going virtual, we've definitely expanded its accessibility. Of the more than 200 registered participants, roughly half are international, not in the US. Virtual meetings also have unique challenges, as I know you're all aware, for keeping things moving smoothly and productively. And we're going to go over some of the technology that we'll be using that will hopefully help us stay on course. And I'd also like to thank you all for agreeing to a code of conduct in your registration. It's so important that we treat each other with respect. And it's the best way we can have a truly fruitful discussion, which is our goal. Okay, so moving on. Why should we study solar minimum? Isn't it boring? These images, of course, are showing you the solar corona in extreme ultraviolet, and they demonstrate how solar activity waxes at solar maximum and wanes at solar minimum. And during solar minimum, it's certainly true that solar flares and coronal mass ejections and associated space weather impacts at the Earth and other planets of that type reach their lowest ebb. However, when things are simple, end-to-end connections are easier to trace. It's also an opportunity to characterize the baseline or ground state of the heliosphere and the planetary environments. So the prior initiatives, solar minimum 1996, 2008, we really saw that solar minima, no two solar minima are the same. It characterized how different they could be. And WHPI, which we're doing now, is proving to be just as unique a time period as WSM and WE before them. So to recap, whole sun month, WSM, was the first of our whole initiatives, and it occurred during what you might call a classic solar minimum. The solar corona was characterized by a global dipole field with streamer belts at the equator and large coronal holes at each pole. The notable exception to these polar coronal holes was an equatorial extension shown here, known as the elephant's trunk, which was the source of a fast solar wind stream, which impacted the Earth during this time period. And the first initiative focused on just one solar rotation during the solar minimum, and it involved 11 solar, 7 solar wind instruments, and about 50 participants. And then in 2008, we launched the whole heliosphere interval, or WHPI. In addition to an expanded scope from sun to Earth, we had a larger group of participants with dozens of solar, heliospheric, and geospace instruments involved. That minimum was surprisingly different than whole sun month. Despite an extremely low number of sunspots, this is the sunspot number here, there was more structure in the corona, certainly in 2008, and the heliosphere. There were multiple broad low latitude coronal holes at that time in 2008 and periodic forcing of the Earth's space environment by high-speed streams. In general, we found that comparing the first two minima was really edifying, especially for understanding sun to Earth processes associated with global heliospheric structure. High-speed solar wind streams occurred during both of those minima, but whole heliospheric interval had much longer lived and coherent low-latitude coronal holes that you can see in these little insets. And as a result, the periodic forcing of the Earth's geomagnetic field and its radiation belt were very evident. We're going to be talking about what we call the WHPI mosaic later in this meeting. And that's like, how do we compare data across the heliosphere and on multiple time scales? This figure is an example of how much can be immediately learned by lining up coronal structures and solar wind streams and then connecting to impacts in a planetary environment. So the minimum of 2008 continued to evolve and become even quieter in 2009. And in the end, it was the longest and deepest minimum witnessed in the space age at that point. With 2009 came a flatter heliospheric current sheet and the disappearance of those low latitude coronal holes that I mentioned and the associated high speed streams. It resulted in an extremely depleted radiation belt at the Earth, as well as weak interplanetary magnetic field, and with it record levels of galactic cosmic rays. But the sun's magnetic field never really became the simple dipole of 1996. And maybe because the polar fields in 2009 were significantly weaker than in 1996. Which brings us now to WHPI, while we're all here. Based on lessons learned, we set the interval for an actual entire year. Participation continues to grow. We list here numbers based on missions, not instruments, of solar, heliospheric, geospace, and planetary. We have more than 600 participants from all over the world on our mailing list. The solar magnetic structure during WHPI is perhaps more like whole sun month than we, in that there's an equatorial streamer belt and large polar coronal holes. So it seems more dipolar, but there's much still to learn, and that's why we're all here. There's a lot to talk about at this workshop. There's science going on all around the world, and we have wonderful data from sun to Earth and to other planets. And so the main goal right now for WHPI is to coordinate and support these efforts in various ways that we describe in our webpage, which please visit if you have not already. You should be able to find it if you search on WHPI. Luckily, it's a pretty good, unique string. Some of you have already started to use our data portal and to gather models and observations, which was the focus of the activity yesterday. And you're going to hear more about it as the week progresses, so don't worry if you weren't involved in yesterday's. So Barbara will bring back to that tomorrow. There's the data portal down here on the webpage. And you're also going to hear more about some of the campaign periods during and just after this WHPI year. With the advent of Parker Solar Probe, we have exciting new solar wind data that connects the sun and planets. So the workshop is organized by 4 working groups, which we're going to be summarizing shortly. We'll have scene setting talks for each of these working groups, and we're going to have sessions that include both focused oral presentations, and in one case we have a panel discussion. Throughout, we're going to be encouraging your ongoing questions and contributions to discussions, which will include extended plenary conversations each day, loosely organized around assessing and evaluating what we are learning about the WHPI period, the model and data assessment. We've kind of organized the plenary discussions on Tuesday and Wednesday with that. And then on seeking connections between the analyses that already exist with the goal of forging collaborations across disciplines. So moving out of this workshop, how can we build? And that on Thursday and Friday is to some extent is going to be our coordinating theme for the plenary discussions. We also have 30 posters, and we've set aside time to meet and discuss them both in plenary, and then we're going to have poster specific breakout rooms. And then lastly, we're going to be having an icebreaker activity today after the talks and the science discussions. And so this will be an opportunity for you to come and meet your colleagues in a more informal and fun gathering. The Zoom chat is available for technical and logistical questions, but if you have science questions during the talks, you should ask them via the Slido platform. And the questions in Slido, they can be answered by the speaker or by other conference participants within that platform at any time. The questions raised in Slido will also be raised by the hosts, the chairs of the sessions during the discussion periods, so that the speakers can answer them out loud and we can have an out loud discussion. So if you're not as comfortable interacting with the written, there will be an opportunity to have verbal discussion and vice versa. If you want to comment on the questions or raise new ones not raised on Slido during a discussion, there's going to be an opportunity to do so during discussion times by raising your hand. That's how you'll be able to unmute and ask a question out loud. So Slido, I keep mentioning, is a platform we use to facilitate and archive our discussions. So to make sure we're ready to use it together, I am going to hand over to Kelvin Tavares, who is our tech support, and he's going to take just a few minutes to go through it with you all. So Kelvin, can I switch over to you?
Yes, thank you, Sarah. Hello, everyone. Let me just go ahead and share our screen here. Can you all see the Slido? So Catherine and I will be posting a link to Slido, and this is Slido. When you come onto this page, if you want to ask a question, you can go ahead and just type it in the type your question field. We would like all of you to also click on the icon here on the top right corner, click on profile. You can put in your name, your email. This is so that we know who has posted the question. So if I go ahead and put my information in here, I'll be able to then type in my question as myself. If for whatever reason you choose to be anonymous, you have the option to do that by just switching to anonymous. So I can just go ahead and send that. As a presenter, if you see a question that you would like to answer, you can just reply to those questions below the reply icon here. Pretty simple to use. Catherine and I will be available for any questions you might have about Slido. If you want to change modes, you can go into dark mode if you like, or light mode. Well, I think that's pretty much it. So I'll give it to Ian and to introduce the rest of the morning session. Thank you. Ian, I think you are muted.
Sorry about that.
There we go.
All right.
We can hear you now.
Okay. Let me start out by welcoming you all to the whole heliosphere and planetary interactions. And this is going to be an overview of the working groups for the whole heliosphere and planetary interactions workshop. And I would like to start with working group 1, Heather Elliott and Carlos Martinez.
Hello. This is working group 1, which is characterizing the whole heliosphere at solar minimum. And my name does have another T on it. And the purpose of this working group is to study the global connected structure of the heliosphere and planetary space environments and atmospheres. And just to set the scene a little bit, I have a plot here of the sunspot number in black, and then a smooth version of sunspot number in red. And in blue, I have the current sheet tilt angle, just to kind of provide some background about solar minimum and the solar cycle. And I think that Carlos is going to go over the schedule.
Yep. Hello, my name is Carlos Martinez. Briefly, I will describe the activities and the talks that we'll have in this working group 1. As Sarah mentioned, there will be a scene setting, a talk given by Pete Riley, where he will talk about the lessons we learned from models and observations. And that will be today. Also today, we will be talking on the first focus topic, that is the Sun heliosphere mosaic. We will have 3 talks, Ian Hewins, Rohit Shiver, and sorry, I get something here. Yeah. And Alberto Vasquez. So these 3 talks will basically explain the Sun heliosphere mosaic. Is a nice view, big view. Then we'll have Parker Solar Probe and MHD model of large-scale structures and turbulent transport. And finally, a 3D tomographic reconstruction of 2 of the WHPI targets. Again, this will be happening today. And next Friday, the second focus topic will be the quiet time impact on planets. So we will be going through different planets in the solar system with talks by Shoa Fang. We talk about Mars, Shuan Kai, the Earth and variability during low solar activity and quiet geometric activity. Then Bernard Jackson, he will talk about scintillation analysis during Bepi Colombo and solar orbiter Venus passes. Pontus Brand will take us outside the solar system and we'll get into the local interstellar medium. It will be nice, a very large extent of sun heliosphere connections. And finally, Dan Gershman, he will talk about effects on the outer planets as well as in Mercury. So we'll be covering basically the entire solar system. This will be followed by a discussion. And the last activity for this working group 1 will be posters. It will be taking place again on Friday. So that's it. Thank you.
Okay, working group 2.
Yeah, hi. So working group 2 will be about high-speed streams. And so high-speed streams are an important phenomenon that touch every aspect of heliophysics. So to begin with, they originate from coronal holes of the sun. Can you go to the next slide? Ian. And so as they expand into the pre-existing solar wind, they form stream engine regions and rotating interaction regions. Go to the next slide. And when they reach planetary bodies, they compress the bow shock and magnetopause. Go to the next slide. So in turn, this then drives geomagnetic storms, which can lead to enhanced wave activity, electron acceleration, and precipitation. Go to the next slide. Which then leads to an increase in temperature and ion outflow. So really, this is a phenomenon that really is in line with the whole WHPI campaign of being whole heliosphere and planetary interactions. So if you go to the next slide. The way we're going to be structuring our session is we have 2 different sessions today and tomorrow, or Thursday. So today from 11:55 to 12:55 p.m. Mountain Time, we'll be talking about coronal holes through interplanetary space. So kind of taking that solar into the solar way standpoint. And then on Thursday, we'll be talking about high-speed streams and their impacts on planetary systems. At the end of that, we're going to have much longer discussion to really then bring all of this back together and view this phenomena in a very whole heliospheric sense. And so with that, please come ready to discuss high-speed streams to our sessions. And we're looking forward to having a really great meeting. So thank you.
All right, thank you, Robert. Working group 3.
Hi, this is working group 3. Working group 3 is a comparative minima. So the goal of this working group 3 is compare the current minima with previous solar minima, and which were including solar activity measure and indices, which includes both solar irradiance indices and the geomagnetic indices, and then the solar wind properties. And another goal is investigate how periods of extremely low solar activity affect the geospace and other planetary space environments. And the next slide. So this is a working group 3 agenda. So we have 2 sessions on Wednesday. First session, 30 minutes scene setting about comparative solar minima, given the two scene setting presentation given by David Hathaway and Janet Kozira, and then 1 hour session for focused topics about the space age solar minima. We have 3 presentations given by Marty Merlenzak, Lan Jen, and Anna Elias, followed by 30 minutes discussion. And then we have another session on Friday. It's 1 hour session. It will be run by a panel format. It is about model minimum, long-term solar variability from historical records and the impact on climate. We have 6 panelists, Natalie Krivova, Judith Lin, Hanli Liu, Matthias Rempel, Leif Svagard, and Ilya Soskin. And then we also have a poster session on Friday that is will be go with working group 1. So that's it. That's our working group 3 agenda. Thanks.
Thank you, Li Ying. Next, working group 4.
Yeah, hi everyone. I'm Rachel Philwood, and I am one of the 2 leaders for working group 4, which is solar activity throughout the heliosphere. Next slide, please. So what is working group 4 going to address? And so the 3 other working groups have a lot of material covered, but we are specifically focusing on coronal mass ejections and solar energetic particle events as they erupt off the sun and then expand out into the heliosphere and affect the planets and the interplanetary medium. And unlike more general CME sessions that you might see at other conferences, we are of course focusing on this activity during solar minimum, which gives us a really great time to look at a single CME without interactions maybe from other solar activity that goes on when we are in a more active sun period. So we're gonna highlight different methods and studies that exemplify how to integrate a wide range of data and modeling sources, which are typically going to be needed if you need to study a CME as it expands out from the sun and out into the heliosphere. And so we're going to showcase results and ongoing work. And there is also in some of these campaign periods of interest that Sarah mentioned earlier, there is a CME event. And so we're going to be focusing on that a little bit as well. Next slide, please. So here are the events lined up that are associated with our working group sessions. So first, tomorrow morning, our plenary is by Christina Lee, and we're really excited to see what she's going to present to us. I think that's going to be very interesting. And then Wednesday, we have our first working group focus session, and it's going to be about connecting activity across the heliosphere. So you see we have a number of different presenters lined up there, and then we're going to have some group discussion at the end. So we have people presenting about both data and modeling, and so it'll be a great time to ask questions about their results and kind of think about how we can start to integrate all these sources together for really interesting studies. And then on Thursday, we have our second time period for our focus topic, and it's going to be looking at these specific events. So like I said, we have these time periods of interest, and so we have 2 speakers coming to talk about that specific time period and time periods like it during solar minimum, and then some more group discussion. Hopefully we'll have gotten to know each other a little bit more and hopefully spawn some collaborations from this session. Next. Yeah, that's it for me. Hope to see you at our working group sessions.
All right, thank you very much, Rachel. I believe Barbara Thompson and I are chairing the next session. Or this session.
Yep.
And Barbara, you want to take over with the introduction?
Sure. So our keynote speaker for working group 1 is Pete Riley. And I am so glad that we got Pete, because Pete was one of the originals that made Whole Sun Month and Blues for Interval really powerful. And so I am really excited to hear what Pete envisions for the next our next WHPI interval. So, and I'll be monitoring the Slido questions. I want to remind you, submit, the link is in the chat. Go to the Slido and I will monitor the questions. And at the end, we will have you either, we'll either have people answering the questions in the chat, or we'll have you ask them out loud. So thanks, Pete.
Okay, thanks, Barbara. Let me see.
You can see the slide set.
Yeah, let me figure out how to go to full screen.
Usually Command Enter, but.
Pete, you can go to slideshow and start from the beginning.
Let's see, slideshow, play from the start.
Yep.
How's that?
That looks
Perfect.
good. Great.
Great. Okay. Thanks, Barbara. Good morning to everyone. It really is great to be at the WHPI workshop, although I really wish I was at the workshop. I think there's definitely something missing from having to do this through a Zoom setting. Of course, I'm giving my presentation on the beach, so even if it's a fake one, it's not too bad. Feel free to interrupt me if you've got any questions or comments. I'd hate to talk for 20 or 30 minutes without somebody calling me on something. So I was asked to provide a scene setting talk characterizing the whole heliosphere at solar minimum and focusing on what we've learned from data and models. So I'm going to focus on the large scale coherent properties of the heliosphere, and I'll limit the domain to within 5 or 10 AU of the sun. I'll also emphasize some of the differences between each of the last 3 solar minima, even though we have a separate session that's focusing on that. I was also asked to include some points about how different planetary space environments respond to the sun at solar minimum. So I will make a few brief comments about that. Now, every mission or observatory can claim that it's revolutionized our understanding about some aspect of heliophysics. And when we're talking about the whole heliosphere, I'd argue that that mission was Ulysses. So we can talk about before Ulysses and after Ulysses. But you could easily make the case that it should be Helios, or Stereo, Parker Solar Probe, or even Mariner 2. But if you'll indulge me and allow me to oversimplify things, before Ulysses, we had a generally 2D picture of the heliosphere in the ecliptic plane. And this is Vic Pizzo's iconic graphic that shows the process of co-rotating interaction regions forming, where the slow wind's overtaken by faster wind, creating a compression region that's bound by forward and reverse waves, which steepen into shocks, typically beyond 1 AU. There are, of course, a lot more details associated with this, such as the development of shear flow at the stream interfaces, the location of the heliospheric current sheet, which would be partially embedded in this 2D cartoon. But I think everyone's got a good understanding of the processes that are captured in this cartoon. So Ulysses, I think, dramatically expanded our view of the heliosphere. And here's the iconic image from that mission. So we're showing solar wind speed as a function of latitude, where the speed is color-coded by the polarity of the interplanetary magnetic field. The green curve is the normalized proton density, and all of this is overlaid over a composite image of EIT, Mauna Loa, and LASCO C2 observations. And Barbara, correct me if I'm wrong, but I think that you gave me this image, right?
Yep.
Yeah.
But you made it powerful.
I think it was great to start with. Now, we could easily spend an hour talking about this picture, but I'll just point out a couple of key points. First, all the action is taking place in a band plus or minus 30 degrees. And that's what Jack Gosling called the band of solar wind variability, which I think is a really good way to describe this. And these data are all from the declining phase of the cycle and at solar minima. You can also see there's an asymmetry between the left and the right. This is just a sampling effect. For the rapid latitude scan on the left, we got more of a snapshot of the stream structure over a few rotations. On the right, there were many, many more solar rotations within this region as the spacecraft was going out or coming from aphelion. One last point to make, though, is that it's easy to dismiss the high-speed solar wind as being boring, but it still has a lot of structure. As an example, the red intervals in the southern hemisphere and the blue intervals in the northern hemisphere are signatures of long-period alphane waves. Now, there have been lots of studies of CIR structure using Ulysses data and other data sets. And I'll just illustrate one that's based on work that Jack Gosling and I did. For each of the CIRs that were in that last slide, I computed the orientation of the forward and reverse shocks to test the predictions that were made by Vic Pizzo's model results. And generally, the 2D picture was supported in the sense that the fronts were tilted roughly along the Parker spiral, as you can see in the lower left. But more importantly, the tilt in the meridional plane was as predicted, and these were based on Vic's 3D calculations more than a decade before the Ulysses observations. So the forward shocks are tilted such that they're propagating towards the equator, and the reverse shocks are propagating towards the pole. Now, to show that that's consistent with global MHD models, here's a set of Mulvide projections at 2.6 AU. The 3 components of the velocity are shown in the top row, and then density, radial field, density, and pressure are shown in the bottom row. And this is for the WSM interval, or the second half of that. And you can see the alternating tilts, particularly in the pressure, are at least qualitatively what you would infer from the in situ measurements. So it all seems to fit together. And if we look at the results in the meridional plane, this shows it even more clearly. These are scaled thermal pressure. And you can see that the CIRs are tilted so that the forward shock normals are pointing towards the equator and the reverse shock normals are pointing towards the poles. When you look at different minima, though, things get a bit more complicated. During the whole heliosphere interval, in 2008, that simple slow flow band was now punctuated by equatorial coronal holes that drove beams of fast wind through the slow wind. And this had the effect of complicating the resulting structure. But it didn't complicate it in a way that we couldn't understand intuitively. So here at the top, there are 4 solar wind profiles close to the sun, assuming that the solar wind could be approximated by a 2-state flow. And that's obviously an oversimplification. The fast wind is the dark gray shaded regions, and the slow wind is light gray. As the wind propagates radial away from the sun, you get compressions and rarefactions forming, and those are marked by the stippled pattern in each of those panels. In terms of how each pattern physically looks in the heliosphere, the CIRs are orientated as shown in the bottom panel. But the takeaway message is that if you know what the driver looks like, say at 30 solar radii, you can easily predict what the structure of the solar wind should be far from the sun, at least in a qualitative sense. So fast forwarding 20 years and skipping a few amazing missions, we can ask how Parker Solar Probe has helped us to understand the structure of the heliosphere. Obviously, the emphasis with this mission is to touch the sun and not really probe its outer reaches, at least directly. So as a demonstration that these models can be validated by comparing with the observations, in this plot I'm comparing model solutions at the time of Parker Solar Probe's 3rd perihelion, which was 3 months prior to the last solar minimum. And in this case, I'm comparing 3 different types of model solutions. I won't go into the details of those. But if we compare speed, radial field, and plasma number density with these 3 model solutions at the location of stereo, and I picked stereo because there was more structure there. So it was more of a definitive test. But you can see that this thermodynamic model captures almost all of the observed stream structure really well. And that's the black curve and the blue curve in the top panel. So it gives us a lot of confidence that the models are useful tools for revealing the underlying global structure that's only hinted at by the in situ measurements. In terms of disagreements, I'll just point out that the model results overestimate the peak densities. Now, in terms of PSP science, an obvious topic to present would be the so-called switchbacks that PSP has seen during each of its solar encounters. But it's not clear how important these are from a whole heliosphere perspective. So instead, I'd just like to briefly mention the amazing images of coronal rays that the WHPI instrument is producing. These are all within less than 1/4 of an AU, and they really can't be seen from 1 AU observatories. Here's an example from a study led by Nicolas Poirier. In the top row is a sequence of WHPI I level 3 images from the first encounter in 2018. The arrows are pointing out specific ray-like features. And then the 2 panels in the lower left show 2 different MHD results, and they're compared with the observations in C. And then finally in the bottom right is a pixel-based comparison of a slice through them. And there seems to be a very good agreement between the model results and the observations, at least for the 2 main coronal rays. I'm not convinced about the microstream, which is the red arrow feature. But as a modeler, I'm the first one to be a skeptic. It's easy to find patterns when you're looking for them. Nevertheless, I think this shows just how much models have improved over the last couple of decades to help us interpret the new data sets. Now, an important part of characterizing the whole heliosphere at solar minimum is to understand what's the same and what's changed from one minimum to the next. And as I mentioned, although there is a specific session on this tomorrow, I just wanted to make a couple of points from a global perspective. And in particular, I'd like to ask, how does the structure of the solar wind, how is it likely different for WHPI as opposed to WSM or WE? So on the left, I'm showing the daily sunspot number in red and the monthly running average in blue. And there are lots of points that could be made, and I'm sure David Hathaway will probably talk about some of them tomorrow. The one I'd like to focus on here, though, is the depth and duration of the troughs at solar minimum, which increases with each minimum to the point that it bottoms out at the beginning of cycles 24 and 25. And you can see that better on the right, where I've aligned each solar maximum as a time 0 and then plotted the evolution from that point. So each curve captures the second half of one cycle and the first half of the next. So you can see that interval 22-23 shows the strongest gradient, both in the decay and rise of sunspot number. Next is 23-24, and then finally 24-25. So based on this, we'd anticipate that the climb out from the solar minimum from December 2019 will be even shallower than either of the two previous solar cycles. But the key takeaway, though, is that it seems that there's a progression of ever decreasing activity, at least based on this. Now, another useful parameter to look at is the solar polar field strength, which we can get from photospheric observations. This complements the sunspot number in the sense that it's a measure of the largest scale magnetic fields that are visible on the sun. So again, to look at this, I'm using values estimated from the Wilcox Solar Observatory. The parameter shown is an average of the line of sight field between 55 degrees to the pole, and it's averaged over 10 days. The figure on the left summarizes the data from the northern polar regions in red and the southern polar regions in blue, and the average of the two is the black curve as a function of time from 1990 to 2020. Again, if we just focus on contrasting the differences between the two minima, the panel on the right does that. And again, the curves have been aligned to the time of each solar maximum. So you can see that the last two solar minimums seem to be very similar, and that these are both substantially different from the 1996 minima. In fact, about 60% of that value. If we move now into the solar wind, in this figure I'm summarizing measurements from the Omni dataset 1AU, solar wind speed, and then radial field and number density. And that's all as a function of time from mid-1996 through November 1996. So a 6-month interval surrounding the minimum. And you can see that there's a clear periodicity in the data, particularly in solar wind speed with the recurrent modest streams, about 500 kilometers per second, that are occurring prior to and following the minimum. After the minimum, the amplitude of the streams increases to about 700 kilometers per second. And you can also see this recurrent patterns visible as sector crossings in the radial magnetic field, which alternates between plus or 5 nanoteslas throughout the interval. And then finally, the compression regions that are created by the streams are clearly visible as peak densities reaching about 30 per cubic centimeter. And it's also worth noting that the base density during this period was consistently about 3 per cubic centimeter. So I could show similar plots for the following two minima, but they're qualitatively very similar, but statistically they're quite different. So to explore this in these three panels, I'm showing histograms of solar wind speed, radial field, and number density for each of the 6-month periods surrounding each minima. You have to be a bit careful when you're interpreting the distributions. The values are a convolution of the plasma's initial properties and its evolution, its passage to 1AU. So as an example, initially slow wind may have been accelerated by faster wind behind it. But some of the points in the curves are still markers of the undisturbed wind. The initial rise in speed, for example, provides a measure of the lowest speed produced at the sun, since there's no other obvious physical process that would act to slow down the slowest plasma. And the slowest densities, which are in fact associated with the fastest solar wind, are also representative of the source values, since the fastest wind can only be slowed down by hitting slower material ahead. So if we look at the solar wind speed, we can see that the initial sharp rise in speed for the three minima is separated by about 20 kilometers per second, but it's not sequential. the base or the floor in the solar wind speed seems to have dropped by 40 kilometers per second between 1996 and 2008, and then rose by half as much for the 2019 minimum. And this ordering is also mirrored in the location of the peak or median values in the speed. If we look at the number densities, we see a similar pattern. The sharp rises on the left of the profiles, they suggest that the total average difference in the base densities of the fast solar wind is about 1.5 to 2 per cubic centimeter. Again, with the decrease occurring from the 1996 minimum to the 2008 minimum, then a rise for approximately half for the 2019 minimum. Can't really make any inferences for the radiomagnetic field, though. So based on the velocity and the density distributions, we can say that the 2008 minimum was truly a substantially new low for the heliosphere, while the 2019 minimum appears to represent a partial recovery. So again, we can look at model results to try to understand the observed properties and the structure of the solar wind. And again, I'm going to skip all the gory details about the modeling, but feel free to ask any questions. If you'd like to know more, but please don't let me try to convince you that the models are right. They're not, they are wrong. But as someone said, occasionally they are useful. The most important thing to take away from the models, though, is that they are driven by the observed photospheric magnetic field, and that's a key parameter for the model. So our MHD calculations are typically driven by either MDI or HMI derived synoptic maps. And you can see here that I've plotted those for each of the 3 solar minima or Carrington rotations representative of them, and saturated to plus or minus 20 Gauss. So comparing the 3 panels, you can see that the polar field strengths are notably larger for the 1912 rotation than for either 2077 or 2224. And that's consistent with the inferences we drew from the Wilcox polar field values. Now, once we have a coronal model run, we can then trace along field lines and compute coronal hole boundaries for each of the minima. Counter rotation 1912/1913 was well studied as part of the WSM interval. And so you can see the so-called elephant's trunk that Sarah mentioned earlier in the northern polar coronal hole, about 270 to 300 degrees longitude, but there are no equatorial coronal holes because of the stronger polar fields. For 2077 and 2224, on the other hand, there were both more equatorial and mid-latitude coronal holes, as well as more structure and penetration into the lower latitude regions. So again, the last 2 minima are more similar to each other and both quite different to WSM. So once we have those coronal solutions, we can calculate boundary conditions for the heliospheric model, and that's shown on the left. So these are our best estimates for the speeds at 30 solar radii. If we look first at the similarities between each of the panels, you can see that we have uniform fast wind dominating over most of the spherical domain, and it's only within this relatively modest band of solar wind variability that there's any structure in the speed of the solar wind. Another point is that there's considerable structure at the boundary between the slow and the fast wind, with a boundary region of increasing speed joining the 2. And as we saw earlier, the orientation of these boundaries as a function of longitude and latitude is what drives the development of the compression and rarefaction regions. Once we've got a set of boundary conditions for the heliospheric model, we can run that forward in time. And on the right, you can see the predicted speed at 1 AU. You can also see there's a sort of strong similarity between the 2. So where the interaction regions form, this distorts the location of the heliospheric current sheet, such as 180 degrees in each of the 3 rotations. And you can also see the erosion of the equatorial sources of the vast solar wind as they're decelerated by the slower wind ahead. So using these model results, we can make a comparable histogram comparison of speed, field, and density. we saw that the observed flora in the solar wind changed in each minimum, as did the flora in the density. But you can see from these distributions that our model has a fixed floor in both speed and density. And this is just an inherent limitation of this semi-empirical model that I've used here. These numbers are essentially free parameters that we can set. Now, we could fix this by developing better free parameters for the two most recent minima. But a much better solution would be not even to use these parameters and use a more self-consistent approach. And we do have such a model, but there are trade-offs with that, especially from a space weather perspective.
Hey, Pete, we have a question that's kind of related to this.
Yes.
It's from Sudeep Mandal. And they ask, we often see an overlap between cycles of 1.5 years. How does that affect your histograms at solar minimum related to the solar wind properties? And I think you were just going over those properties.
Oh, so is the question whether or not it's a good approximation to lump together data that might actually be more representative of the beginning of the next cycle with the previous cycle?
Yeah, I think they're trying to figure out how you distinguish, or if not distinguishing can throw it off, something like that.
Yeah, it certainly could. I mean, this is a very first cut at trying to look for differences between either of the cycles. When I made those histograms, I did actually create intervals of different duration. So I looked at 3 months, 6 months, and even 9 months, and I slid that window along just to make sure that I wasn't picking an interval that was perhaps keyed into some specific feature. For example, if in the 1996 minimum there was coronal structure that persisted for 6 months, that might drive those histograms to look in a particular way that wasn't representative of that time period, in the sense that it's statistically captured it. And I didn't see any differences from doing that.
Okay, so
but yeah, I guess I do appreciate the point. Yeah.
Yeah, you did a sensitivity test and it wasn't super sensitive. Okay.
Exactly.
Okay.
Yep. Okay, so in the last few minutes that I've got, and I apologize that I can't do justice to this in 5 minutes. But I think most of us are familiar with the interaction of the Earth's magnetosphere with the solar wind. Generally, in the absence of CMEs, we observe relatively modest geomagnetic storms that are driven by high-speed streams. They're often recurrent as the sun rotates every 27 days. But how do other planets respond to this driver? And I am certainly not an expert in this area. But I've separated the responses into 2 main classes. First, the role of the solar wind itself plays, and then second, the role the planet itself plays. So if we start with the solar wind, the first thing that we need to appreciate is that because of its spherical expansion, its properties change dramatically from the sun to, say, 10 AU. And here's a plot from a recent study that shows that although solar wind speed is approximately constant over large distances, the magnetic field strength, which falls off either as 1/r, 1/r squared, depending on which component you care about, and the density, which falls off as 1/r squared, they fall by orders of magnitude. So this in turn means that the Alfvén speed drops from about 100 kilometers per second at Mercury to less than 40 kilometers by the time you get to the orbit of Jupiter. And perhaps more importantly, the Alfvén Mach number of the solar wind changes from about 4 at Mercury to over 11 by the time you get to Jupiter. So back in the early 60s, there were 2 main ideas about how energy could be transferred from the solar wind to the magnetosphere and ionosphere. One was based on magnetic reconnection in the magnetopores and in the tail, and the other was based on a viscous interaction mediated presumably by a Kelvin-Helmholtz instability. So it turns out that the reconnection electric field is proportional to the Alfvén speed, but the Kelvin-Helmholtz instability parameter is proportional to the square of the Alfvén speed. The net effect of that is that as you move outwards away from the sun, the relative role of reconnection versus viscous interaction shifts. So although reconnection perhaps dominates at 1 AU by as much as 90% in terms of the energy transfer, it becomes less important as you move further away from the sun. But the other part is that the quiescent solar wind isn't just single valued. As we know, there's lots of stream structure embedded within it. So how do we expect that it will evolve as you move farther and farther from the sun to the outer boundaries of the solar system? So observationally, we don't have measurements at all heliocentric distances at the minimum of the activity cycle. But Voyager 2 did collect data from about 13 to 25 AU around the period of the 1986 minimum. And I've plotted that here. Speed, the N component of the field, are roughly the north-south field, and the density. And looking at the speed, you can see that the overall amplitude of the fluctuations decreases with distance, although that could be a temporal variation. But you can also see the amplitude of the field and density decreases too. And that's exactly what you'd expect, even from the simplest 1D hydrodynamic models of high-speed streams. This is from a paper from Art Hundhausen back in the 1970s, but was modified by Jack Gosling in a review paper. And you can see that a single high-speed stream accelerates as it moves out, a forward-reverse shock pair bounding the leading edge where the compression region is, forms, and they steepen into a shock somewhere beyond 1 AU. But the main point is that although they're developing stronger shocks, the amplitude of the fluctuations is decreasing with increasing distance. And this is even more striking for the compression region, which must contend with the spherical expansion of the solar wind. The other main factor that we should consider is how each planet is unique and will respond differently, even to the same solar wind profile. And again, I have no time to go into any meaningful detail. But the first point I'd like to make is that the scale size of the planets varies massively from one to another. The inset box here shows the scale of Mercury to Earth, Earth to Uranus and Neptune, and Uranus and Neptune to Jupiter. So the power in the fluctuations at different scales in the solar wind should be important in terms of how the solar wind interacts with each planet. A second point is that some of the planets have magnetic fields and some of them don't. And that will obviously have a big effect on the interaction with the solar wind. A third point relates to whether the planet has an atmosphere and or ionosphere. And a fourth and final point relates to the orientation of the planet's magnetic field, if it has one. So most have an axis that's at least roughly aligned with the sun's rotation axis, but Uranus and Neptune are strongly inclined. So to summarize, over the years, I think models have been crucial for understanding the observed properties and the structure of the inner heliosphere. Of course, I'm biased. In terms of how the WHPI interval differs from WHI and WSM, on one hand, we have the solar indices like sunspot number and to a lesser extent the polar field strength that suggests we're sliding into a deeper, quieter epoch, perhaps becoming a grand minimum. But on the other hand, we have the statistical properties of the solar wind that suggest the most recent minimum was in between the conditions for the 1996 and 2008 minimum. Structurally, there's a clear distinction between the 1996 minimum and the two that followed it, with the appearance of more pseudo-streamer structure, equatorial coronal holes, both of which were facilitated by a weaker polar fields. And then finally, and as a clear oversimplification of the problem, we can appreciate that planets will interact with the solar wind depending on the properties of the solar wind as determined by the distance of the planet from the sun and the intrinsic properties of the planet itself. And then finally, where next? In terms of new missions, Solar Orbiter is starting to produce a wide range of interesting data sets, as well as the usual in situ magnetometer and plasma measurements. There's the polarimetric and helioseismic imager, or PHI. PHI is actually made of two telescopes. One is the full disk telescope, and that covers the entire solar disk, all phases of the orbit. And the other is the high resolution telescope that claims it can resolve structures as small as a couple of kilometers on the sun at closest perihelion. So as modelers, we're really excited about getting magnetograms away from the Sun-Earth line to splice into our current maps. We also shouldn't forget about the oldies but goodies. I think data from Ulysses, Stereo, and Helios still hold some interesting nuggets that are just waiting to be mined. A great example of this is related to the recently rediscovered switchbacks in the PSP observations. People had already seen and interpreted this kind of structure, perhaps in different ways in the Helios and Ulysses data sets. And finally, although there are many questions we could ask about the structure and properties of the heliosphere, I think one that is relevant to this workshop in particular, and to the field in general, is how the heliosphere is going to respond to secular changes in the structure of the solar corona. We've seen this just over the last 3 minima. What we're going to see if the sun either restarts activity or drops further into ever weaker cycles. That's it. Thanks.
Great, thanks. If you can unmute, go ahead, and you can also a symbol, a flag, I guess a raise hand for applause. I don't know. So thank you, Pete. That was excellent. So we have a couple of questions. I have the first one I think is relevant to what you recently said. Sarah Gibson had a question about the structural properties of solar min. Sarah, do you want to ask it? And Janet, Janet Lumen, we're very close to the time, so Janet, be ready, be on deck, ready to go.
All right, cool. Yeah, I had a question very briefly, Pete. You know, I commented that when I did my first look at the Mauna Loa data, it looked like this minimum was much more tight and dipolar. And yet that's different, but you've been commenting that the polar magnetic field is actually weak, this minimum, like the one in 2008-9, as opposed to the one in 1996. Do you have any comments on that?
No, I'd have to look at the Mauna Loa data that you looked at as well. If you're looking systematically over multiple rotations, then we have a bit of a quandary. But I could easily imagine that if you're looking at certain images, it could give one appearance or another.
Yeah, I agree. I actually, and that's why I commented at first glance. And so I think that that'll be a good thing this week to dig a little deeper into. So perhaps I misstated when I said earlier, it was more like the 96 in that respect. I need to look at the full period a little more closely. But
yeah, so
look at.
Yeah, so I think it is interesting to characterize the most recent solar minimum and compare and contrast it with the last two. I think because of the maturity of the space era leading up to the 1996 minimum, I think that we began to see that as being usual, and then 2008 was very unusual, and 2019 seems unusual. But in terms of average properties over several centuries, it may be that the 2019 minimum was more usual than unusual, and that we have a slight bias because of that 1996 minimum, or not the minimum as much as the decline into the minimum.
Okay, and then there are several more questions, Pete. I hope you're going to be willing to answer on the Slido as well. You can reply to them. But there's one that's quite popular based on the beginning. Noor and Sarah both kind of had similar questions. And since we're running out of time, I hope you don't mind, Noor, if I ask for him for you. It's the PSP, Helios, Solar Orbiter have all shown that about the small scale structures. You made a comment about this earlier. And both Sarah and Noor were wondering, the MHD models really don't capture that small scale. Is it possible for MHD models to improve to the point where they could have small scale structures? Is it a matter of physics? Is it a matter of observations?
Yes, great question. And obviously there's a certain amount of bias there, because since the MHD models are really trying to understand meso and large scale structure, that they tend to maybe not consciously, but discount the importance of that smaller scale stuff. I think it's a combination of improving the physics and the resolution and the algorithms in the code if we really want to go after some of that stuff. Yeah, at the moment, things like the switchbacks and the role that they play are only treated in a statistical sense in the global models. Victor Ravi has done some really nice work where he's incorporated, at least in a statistical way, the likely influence of the switchbacks. But our models can't directly address them yet, although it's not to say that we haven't tried. We definitely have, and we do have a few case studies that show, look, it might be plausible that we can generate these features.
Well, thanks to everyone else who had questions. We will have this discussion after the next, the working group 2 scene setting talks and the break after that. So the next speaker is Janet Lumen, who is also someone who has been working on this long-term problem with us for a couple of solar cycles. And so I'm very happy to have Janet. Let's see, so if you can share your screen.
Okay.
Janet's going to talk about solar cycle variability in coronal holes and their effects on solar wind sources. And I'll remind you that working group 2 is the origins and impacts of high-speed solar streams. And so this is very germane to the topic. Keep asking your questions in Slido. They will either be answered in text by the speakers, or they will be discussed after the break, or if there's time after the talks. So are you able to share? Okay, Janet?
I'm trying. Let me see if this works.
Looks like it. Looks like it. There you go. Got it. Okay, I can see your desktop.
Okay, let me get this PowerPoint full screen if I can. Come on.
Sure, Janet, you can click the little icon at the bottom there next to the.
Hold on, I think I'm okay here. Let's see, view.
You can click on slideshow right up there.
Yeah, I'm looking for my slideshow button. There it is. Okay.
Start from beginning.
All right. Okay, so I think I'm one slide in. Let's see if I can reverse here. Okay. So I was asked to talk about a lot of stuff too, and Pete covered a lot of ground in his time that I'm grateful for. I'm hoping I can jump in here with a focused discussion of the connection between coronal holes and high-speed streams, and leave the planetary impact to some future speakers. So what I wanted to emphasize is that we have a very limited perspective on the solar wind with our in situ data being stuck for the most part in the ecliptic. And it just happens to be one of the most complicated places to sample and to observe the solar wind. Of course, there are transient contributions to these time series from coronal mass ejections throughout the cycle, but especially at solar maximum, that are usually not cleaned out when we view it. And so therefore, when you look at these time series of magnetic field strength, velocity, and density, the magnetic field is really the only thing that shows the clear solar cycle signature. And that's because everything is all mixed together. And what we try to do in understanding what's going on is to sort through the time series and see if we can refer it back to what's observed on the sun and what we can do with use models to our advantage to do this. So I'm going to be using a time scale, which is a Carrington rotation time, because it's very convenient for the kind of synoptic work that we've been doing. And as Pete says, not all cycles are created equal. And I'm constantly frustrated by the fact that we have so few to look at, and that the human life and the space age combined to keep us limited to only a couple. And we have to keep that perspective in mind all the time. So we have basically the most recent 2 or 3 cycles, maybe a fourth, with which to work. And so we have to look at those as a set in order to get a real perspective on what's happening with the coronal holes and the high-speed streams. Now, we all know by this time that there are multiple sources of solar wind. I try to always promote the idea that the tilted dipole model is to be erased from your mind, and that one should really be thinking of the corona as having polar coronal holes and extensions and mid and low latitude coronal holes. And as the cycle progresses, the polar holes grow and shrink, and the mid latitude and extension coronal holes have their own cycles as well. And of course, there are these helmet streamer and pseudo streamer stacks and boundaries that are creating the blobs and the switchbacks and all of the other things that we tend to see, especially in the ecliptic plane, that the models don't quite yet address yet. But we need to keep in mind that any boundary is likely to be contaminated to some degree or dominated to some degree by this transient component that we don't take into account. So I'm a huge fan of potential field source surface models. And over the years, Neil Shealy and Yiming Wang in particular have exploited this model to the nth degree to really teach us about the corona and the solar wind extension and even F10.7. We are really lucky to have this, and I encourage anyone who works in the field to learn to play with potential field source service models so that you can get an idea at any point in time of what when you look at a solar image, where are you really connected? And a magnetogram is, of course, key to running these models. What we have here, of course, is what you've seen before in previous speaker slides, the blue helmet streamer field lines that come from the canonical Gong website pictures, the north and south, the outward and inward polarities of the open field regions, and in the bottom, the mapping of the along field lines of the coronal magnetic field and the potential field source surface model to the, in this case, the equator, which is a proxy for the ecliptic plane in our studies, and the heliospheric current sheet in blue on the source surface. So you can see right off the bat that from this lower left image that connections to the sun, from the sun to the ecliptic, are here and often dominated by connections to low latitude open field regions, at least in the, as far as limitations of the model, being able to reproduce them accurately are concerned. But it turns out that this model has done a remarkable job of describing what is observed. And two ways we like to use it and to visualize what it's doing and where all these structures are is to look at things in two ways. We can unpeel the sphere of the potential field models, and we can also look at the equatorial slice of what's happening in these models to get an idea of what's going on in the ecliptic. And so the types of plots that some of you may be familiar with, but others may not, that I'm going to be showing are those two varieties. They're either unpeeled spheres that are concatenated by time with sequential Carrington rotations and squashed together, or they are what's happening in the equatorial cut of the model, which is a proxy for what's happening in the ecliptic plane in L1 data, for example, the Omni data set. So for example, these pictures that Jan Lee made from the Omni data set show an example of the latter type of plot. The vertical axis is basically the day of Carrington rotation, and the horizontal axis is the Carrington rotation time. So the time series basically go from bottom to top, bottom to top, bottom to top as Carrington rotations tick along. And in the very top, you can see the polarity of the interplanetary field for cycles 23 and 24. The corresponding density at the L1 point that go with those polarity structures. The velocity showing the high-speed streams, the topic, a focus of this talk in red, and how they fit, how they're sandwiched within the polarity pattern, as well as the density compression that corresponds to their existence, and also the magnetic field magnitude, which reflects the density compression as well on the bottom. And you can see, even with just these two cycles, that there are differences in what's happening at solar maximum and solar minimum, and there are differences between cycles that remain to be fully understood. But it gives us a chance to use the models to take a look at what's happening in the global sun and in the ecliptic, and to try to put it all together. So here's the other type of picture, which is the unpeeling of the sphere of the model. And here on the left, for the almost 5 cycles that we have now worth of data, or 5 decades worth of data to look at, we have the footprints of the open field regions from the potential field source surface model, all in the global map, squashed end to end, for all the Carrington rotations since Carrington rotation 1600 up to almost the present. And they're color-coded according to whether it's a Mount Wilson Observatory magnetogram synoptic map that was used in red, or a Gong one in green or black. And on the right, you have the sunspot number. So what you get a feeling for already from this picture and the use of the models and the magnetograms that underlie them are that the polar holes are seen at the very tops and the bottoms of each panel, and they come and go and vanish briefly during the solar maximum when the polarity is switching. And then you see a low latitude band, which corresponds basically to the active region belts, where that pops up. And then you see all the extensions, the polar hole extensions that are drawn down toward the ecliptic. Now, of course, this is based on a constant source surface height of 2.5 solar radii, and it's spherical. And so there are issues with the details of potential field models. But qualitatively speaking, this is probably, and it seems to be, from the data comparison, as you'll see, a good representation of what's feeding not only the ecliptic plane, but the global heliosphere. And
Hi, is that my internet dropping out or Janet's?
That's Janet's.
Oh, no.
Yep.
Well, I was about to give Janet the couple-minute warning. Hopefully she'll be able to come back on. If not, we do have the break. After the break, we'll be able to have, I think, Janet just finish up a bit after that. So why don't we, let's see, did Janet drop out now?
It looks to me like she did drop out. So I will try to get her back.
Okay, well, I think Nicholas Weedson, are you Weedson, are you here?
Yes, I'm here.
Are you ready to go?
Yeah, sure.
I think, okay, great. So I'm so glad you're here to give this talk. You're going to talk about the modeling of acceleration and transport of energetic particles in the vicinity of high-speed streams. And so this is it's a good topic, especially for the Parker.
I think Janet's back.
Okay, Janet, if you don't mind, can we continue your talk after the break, just because we've already queued up Nicholas? Okay, all right, thank you very much. All right,
sure.
All right, go ahead, Nicholas.
Okay. So you can see my screen?
Yes, we can see it.
Yep.
Okay, perfect. So yeah, first of all, thank you for giving me the opportunity to give a presentation here. So I will be indeed talking about the modeling of energetic particles near high-speed streams. And so let me start with a brief introduction. So yeah, as I was already discussed in quite some detail today, these high-speed streams that can give rise to co-rotating interaction regions. And these CIRs are sometimes seen accompanied by suprathermal particle populations, which are believed to be accelerated by these CIR structures. So they can, for example, or it's believed that they can, for example, accelerate through a first order Fermi acceleration process occurring at the compression waves that bound the CIR, or alternatively, or additionally, they can also accelerate stochastically in CIR turbulence, for example, due to wave particle interactions. Now, when modeling energetic particles near CIRs, it's of course also quite important to have first a good model for the solar wind and CIRs first. And I'm also happy that this was already discussed in some detail by Pete, so I can go fast over this slide. So one of the ways to model the CIR in 3 dimensions is, for example, by using some MHD model of the inner heliosphere. And I've listed here a few of these existing MHD models. And the model that I've myself been using, and which I will also show some results from in the next couple of slides, is the Euphoria model, which is also an ideal MHD model of the inner heliosphere. Now, in order to capture or to try and model also then the energetic particle component, you can then couple a transport model to these MHD solar wind models. There exist a couple of models like that. And in the next couple of slides, I will show you some of the results of a Paradise model, which is a model that is coupled to the Euphoria solar wind model. And it's a model with which I have, over the last few years, studied the propagation of energetic particles near high-speed solar wind streams. And in the first study, we looked, for example, at a case where you actually have a synthetic kind of setup. So this was not based on any real event or a real magnetogram, but instead we used Euphoria to generate a slow wind of 330 kilometers per second with an embedded fast solar wind stream of 660 kilometers per second. So if we go back to this diagram from Riley et al., we are in the situation where you have some kind of, let's say, coronal hole that is close or centered on the solar equatorial plane, and then it's causing this high-speed stream, as you can see in this figure here. So this is about the Euphoria solar wind, and then we use Paradise, the Paradise model, to basically inject energetic particles into this solar wind. And then the focused transport equation is basically solved. So we propagate these energetic particles through the solar wind of Euphoria. And in this study in particular, we actually looked at particles that were coming from the sun, so solar energetic particles. So here we are not directly looking at particles that are being generated by the CIR itself, but I will talk later about these kind of simulations. So we injected 4 MeV protons, and we injected them from the inner boundary from different kind of injection regions to study basically how the presence of this high-speed solar wind stream affect these solar energetic particles. So we had, for example, an injection region in front of the high-speed stream and also an injection region inside the high-speed stream. Now, when doing these Paradise simulations, you also have to prescribe some scattering conditions for the particles to mimic the effect of turbulence on the energetic particles. And in these simulations, this was done by prescribing a constant radial mean-free path of 0.3 astronomical unit. We also had some cross-field diffusion, but we kept this quite low. You can see that the perpendicular mean-free path is 4 orders of magnitude smaller than the parallel mean-free path, meaning that in these simulations, particles were mainly propagating along the interplanetary magnetic field. And if we then look at some of the results of these simulations, so let's first look at the case where we inject energetic particles in front of a high-speed stream. Then, of course, we inject them in front of the high-speed stream, but the magnetic field lines will connect to this CIR, and the energetic particles that propagate along these interplanetary magnetic field lines will also enter the CIR. So in this figure in the background, you see the latitudinal component of the magnetic field, which nicely illustrates where the location of the CIR is as this black and white structure here. So the forward shock is, for example, located here, deflecting the interplanetary magnetic field northward in this case, and the reverse shock is located here with the stream interface being centered or inside the CIR. And so here you can see the contour plots or some of the contour plots of the energetic particles. You can see that the particle or the maximum intensities are obtained close to the forward shock in this case. So where the plasma is also getting compressed, you of course also get that the magnetic field lines are getting compressed, and so also the energetic particles gets compressed towards each other. You also have some southward deflection here, which is due to the forward shock deflecting the magnetic the particles, or the forward shock deflecting the interplanetary magnetic field better in the southward direction. Now, if you look at another simulation at the case where we have the particles being injected in the fast solar wind stream, then we get the picture that you see here. So in this case, in the background, you see the magnetic field strength. The CIR is again seen as this region of very strong magnetic field. So you have compressed magnetic field. So this is the white region. And then behind the fast solar wind stream, you have this dark region where you are in the rarefaction region, which is characterized by a weaker magnetic field. And a result of this rarefaction region is also that the particles are getting spread out over a much larger region in the heliosphere. As a result, the intensities are also lower. But again, some of the interplanetary magnetic field lines will connect the injection region to the reverse shock in this case. And as a result, some particles, energetic particles, will enter the CIR, and you see that the peak intensity of the particles is this time obtained at the reverse shock, which is located here. So these were all studies looking at energetic particles coming from the sun and how the high-speed streams can affect their transport. We also looked at the CIR observed in September 2019, and this CIR event was accompanied by energetic particle enhancements. Now, in this case, we believe, of course, that these energetic particle enhancements were not originating from the sun, but they were generated by the CIR itself. And so the CIR, in the particular CIR, was observed at a moment where both PSP and stereo A were approximately radially aligned, as you can see in this figure here. So again, we first tried to model this, the solar wind, by using the euphoria model. And you can see the results of the simulation here. So the red curve gives the euphoria solar wind speed at the location of Parker's solar probe and stereo A. And the blue dots represent here the data points, so the solar wind speed that was measured by these two spacecraft. To give you a better idea of how the solar wind speed structure looked, at least in the simulation, you can see here the solar wind speed shown in a latitudinal slice of 2.3 astronomic degrees. This was a latitudinal slice where both spacecraft, so both PSP and stereo A, were located, and you can see how the spacecraft crossed this high-speed stream indicated in red here. So that's about, or that gives you a two-dimensional picture of the high-speed stream. If we look at the spherical slice, for example, at 1.5 astronomical units, we get a more three-dimensional idea of the high-speed stream configuration. Now, in this case, these symbols indicate the magnetic connection of the spacecraft through this location. And you can see that we are now in the situation where this high-speed stream is really an extension, actually, of this, this high-speed stream that covers the northern hemisphere. Also very interesting is to look at the divergence of the solar wind velocity vector, because where you have a negative divergence, you actually have converging flows. So these are the regions where you have compression waves which can also then accelerate particles through a first order Fermi acceleration mechanism or just compressional acceleration. And so this quantity nicely shows you the location also of the forward compression wave, in this case which is located here, and the reverse compression wave, which is a bit stronger. You can also see that in the solar wind, there are actually quite a lot of these dual structure where you often have like a forward compression wave and a somewhat stronger reverse compression wave. And so to model the energetic particles that were observed during this event, we used, again, the Paradise model. We injected 40 keV protons continuously into the forward and the reverse compression waves that were bounding the CIR, and we assumed the scattering conditions that you can see here. Now, in this figure, you can see what how the energetic particles that were actually observed by stereo A, with energies ranging from 90 keV up to 1.5 MeV, and the simulation results of Paradise can be seen here. So what you can see is that in this case, the data and the simulation agree quite well. So if we, for example, reproduce this double peak structure, where the first peak is due to particle acceleration occurring at the forward compression wave, and the other peak is due to particle acceleration occurring at the reverse compression wave. The forward compression wave is a bit of it's a bit weaker, and as a result of that, it has a softer energy spectrum, whereas the reverse compression wave is accelerating particles much more efficiently. And also the onset time and end time agree reasonably well, at least at the location of stereo A. Because if we go to Parker's Solar Probe and we compare the simulation results with the count rate that of the EPI-low instrument, then you can see, well, there are some data gaps in the PSP data because the instruments were shut off at these times, but it seems to indicate at least that the simulated intensity, which is indicated in red here, occurs too late in the simulation. But if you shift it by 18 hours, you get a qualitative match between the simulations and the observations. Now, this 18 hours is not very surprising. If you believe that the speed gradient at PSP, so the solar wind speed gradient at PSP must already have been quite steep, meaning that there was a quite sharp transition between the slow and the fast solar wind sources. Because if you, for example, assume that the speed profile at the location of PSP would already have been as steep as it was at the location of stereo A, then you see that you basically shift the peak of solar wind speed, or the time at which this peak is obtained, by exactly also 18 hours. So this is a nice correspondence then. And so I will conclude with one final or two final figures, also giving you or showing in more detail the complexity of the latitudinal structuring of these energetic particle populations. So what you can see here in gray shades are the energetic particle intensities plotted on top of the solar wind speed. And you can see how the shape basically of these energetic particle dense profiles is largely modulated by the shape of the underlying high speed stream. So at 1.5 astronomical units, you have one population centered on the reverse compression wave and one population of energetic particles centered on the forward compression wave. Closer in, at 0.5 AU, you see that these peaks are actually shifted into the fast solar wind and the slow solar wind ahead of the high speed stream. And so with that, I would like to conclude. I've a brief summary. So I've shown some modeling efforts where we have used an MHD code together with a particle transport code in order to try and understand the CIR events in more detail. Well, we looked actually at two different cases. So one situation where we actually study how these CIRs or high-speed streams and more generally can affect energetic particles coming from the sun. So they can, for example, affect them by influencing the spread of these solar energetic particles. They can re-accelerating them, they can trap them magnetically in the inner heliosphere, and they can also enhance guiding center drifts. And then we also did some case study of a CIR event where the particles were likely generated by the CIR itself. And so these modeling efforts kind of indicated that there was likely for this event a sharp transition between the fast and the slow solar wind sources. And because of that, you had quite steep compression waves already within 1 astronomical units, which were able to accelerate the particles. So for this CIR event, we believe that the particle acceleration was mainly due to a first order Fermi-like acceleration process at the compression waves. And the study also kind of indicated how this complex solar wind, three-dimensional solar wind, can also produce, of course, these complex looking particle distributions. And with that, I would like to thank you for your attention.
Excellent. Thank you very much. So I hope you're going to be around after the break so we can handle some questions. Janet, I think you were kind of near the end. Would you be able to just finish the talk now so that we'd be able to start into the questions after the break? What's your preference?
I probably need about 10 minutes.
Oh, okay. All right, then definitely we do the break right now.
Okay.
All right, great. Thank you. All right, so everyone, it's a 15-minute break. Please come back, I guess, in 14 minutes.
Yep, we're going to start right on time.